Okay, so I think we can start. All right, thank you all for joining remotely and coming to this seminar series. So the idea is to have remote seminars weekly, at least for now, while we're all sort of stuck in our places and travel constrained. And then maybe in the future we'll see how to organize this. So this is an inaugural talk, a bit of a test talk. So we'll see if the system is working well and all this. So please, stress test it, ask questions in the end, interact, and so on. John has been super nice in agreeing to giving this inaugural talk, and he's sort of the beta tester for all of this. I actually asked John specifically to talk about this paper because I saw the announcement. I was quite excited about it. I wanted to learn about it. John is an assistant professor in NYU. He's part of the math department at Courant and the Center for Data Science. I was extremely lucky to be able to have worked with him while he was a student at MIT, and I was at MIT, and we've been working ever since. And yeah, he's going to tell us about matrix concentration for products. Thanks so much, and it's all yours. Take around 50-55 minutes.
Wonderful, great. Thank you so much, Afonso, and thank you all for being here. It is a pleasure to be digitally part of the MAD-Z Plus seminar. So I appreciate you all coming. So today I'm going to talk about some concentration questions involving products of random matrices. This is pretty recent work with a bunch of great co-authors, De Huang and Joel Trop, who are at Caltech, and Henriksen Ward, who is at UT Austin. So a lot of the ideas in probability theory over the last several decades have been driven by questions of the following type. If I have a nice function of a lot of IID random variables, when is that function well concentrated around its expectation? So we now have very sophisticated ways to answer questions of this type, and it's led to the outgrowth of the whole theory of concentration of measure, which has been pursued by people like Gromov, Millman, Talleyrand, Ledoux, and so on. And we now, I would say, have extremely sophisticated tools to answer questions of this type. So there's a quote I like from Ledoux's Concentration of Measure book, where he points out that the key property that seems to matter is that functions that have small local oscillations, so that are locally well behaved, are almost constant if they're functions of a large number of random variables, meaning that they concentrate very well around their expectation. So one strand that has arisen over the past 20 years or so has been to ask, to what extent can analogous questions be answered for functions of independent random matrices? So these two questions look superficially similar, but it turns out that there's a real gulf in our understanding between what we know for the scalar case and what we understand for the matrix case. And a meta question, if you will, over the past couple of years, since at least 2010, has been, when can we translate things that we understand from the scalar context to the analogous setting in the matrix context? More specifically, if we have a good concentration bound for scalar random variables, can we obtain an analogous bound when we use matrices instead? So to give a very probably familiar example of this phenomenon, let's just look at the simplest possible setting that we can imagine, which is where the function f is just the sum of random variables. So just in the scalar case here, we all understand this situation extremely well. If I have a set of independent mean zero random variables that are all bounded, say, then one can show via Bernsteins Inequality that the probability that the average of these random variables deviates from its expectation, which is 0, decreases exponentially with the size of the deviation. And in fact, we have pretty precise control over the tails, where we see not only the fact that the variables are bounded showing up, but also we see that we gain something as long as these variables have small variance. So this Bernstein's inequality is a first example of a non-asymptotic concentration inequality. We have non-asymptotic dependence on n, t, and sigma squared, and we get an explicit tail bound depending on the size of the deviation that we measure. And the proof, which is familiar to everyone here, probably uses Laplace's method. It just says, let's pass to the exponential scale and bound the moment generating function of this sum. And the key insight, which is really nothing more than a obvious identity, is that if the random variables xi are independent, then the moment generating function of the sum is just the product of the moment generating functions of the individual summands. And these I can control easily based on the fact that the xi are bounded. So if I have this information about each individual summand, I can bound the moment generating function of the sum, and then I can just use Markov's inequality to obtain this bound. So the natural question, since this is the simplest possible function one can imagine, the average of random variables, is can we say the analogous thing in the matrix case? So here, what have I changed? Now these are d by d independent random matrices. Their expectation is still 0, and I require that their spectral norm is bounded. I'll always use these unadorned double bars just to mean the spectral norm or operator norm of these random matrices. So I have bounded random matrices, and I ask the same question. Is it possible to obtain a bound on the probability that this object, this average, deviates in spectral norm from its expectation by too much? So of course, this is a question I would say that is on its face mathematically interesting. It has some nice aesthetic properties, but the real reason for the growth of questions of this kind, at least in the community that I'm a part of, is because this is a very, very useful object to bound in a lot of applications. So to give the simplest possible example, an object like this shows up whenever I'm attempting to estimate the covariance of a random variable. These outer products of the random variable are just IID matrices, and I might ask how well I can estimate them using a bound of this type. Bounds of this type are useful in study of random graphs, sparsification, randomized linear algebra, kernel methods, dimensionality reduction. I think that if you just look at the flowering of work on sums of random matrices, you'll see that the number of applications seems to be growing even faster than the number of results. People find use for this sort of thing all the time.
So can I ask a question at
Yes.
this stage? So Christoph Schwab is asking, so you just write here independent, but you mean identically distributed, or?
So no, I actually don't need identically distributed here, as long as they each satisfy this almost sure boundedness and each are mean 0, then I don't require that they have the same distribution.
All right, thank you. And you don't impose further structure, because when you say covariance estimation, of course, you have d by d symmetric positive semi-definite, right?
Right. Yeah. So
you...
for now, it turns out that you can answer this question in full generality without making any symmetry or even PSD or symmetry assumptions. I will maybe talk at the very end about how things change for our results with PSD matrices, but for now, let's assume no other structure.
All right.
0, bounded, nothing more than this.
Okay, thanks.
And that's a good point, actually. So one of the utilities of Bernstein's inequality in the scalar case is that we make as few structural assumptions on the random variables as possible. And while we might hope for something better if we assume more structure, it's good to ask at the outset whether we can get away with just this. And indeed we can. So right, there's a number of reasons to ask questions of this type, but understanding this is a relatively recent thing, actually. It was a breakthrough about now 10 years ago, due independently to, let me just say also why this is maybe a hard question originally. You might first hope that perhaps we can just walk down the road that we walk down for scalar random variables, apply Laplace's method, and use an analogous bound. The problem is that we fail at the first step. If I try to take the matrix exponential of these matrices xi, then this identity, which was trivial in the case of scalar random variables, is simply not true in the case of matrices. It's not the case that this Laplace's method allows me to pull the sum outside and bound the product bound each term in the product individually. This is false unless all of these random matrices commute almost surely. So if I am in a non-commutative situation, which is the typical situation for random matrices, this very first idea already fails. So this is why we need maybe something deeper, some new ideas for understanding sums of random matrices. And as I was about to say, that's why it was a breakthrough from about now 10 years ago, due independently to Oliveira and Trapp, showing that you can recover something that looks essentially exactly like the scalar concentration bound in the matrix setting. So just to parse what we see here, notice that apart from the factor of d in the tail bound, which is right here, all of the terms look exactly the same. The tail bound looks the same, the constants are the same, and the role of the variance is now played by the natural object in the case of matrices. Instead of just the sum of the squares of the random variables, I have the sum of the expected squares of the matrices. And to the question earlier about symmetry, if my xi's are not symmetric, then a priori there are two different ways of forming the square of a random matrix, and sigma squared pays for whichever one of these two ways is larger. So the point is that we have a scalar concentration inequality that exactly gives us the corresponding thing for matrices, but we need a new idea. Essentially, the insight of Oliveira and Trop is that you could not just apply Laplace's method, but you need some deeper technology from the study of matrices. And that inequality looks, I would say, deceptively similar to the equality that one uses in the scalar case, but this inequality that we use in the bound is substantially deeper than the identity that comes up in the scalar case. So this is by now well understood, but the takeaway message here is that even for this very, very simple case, for sums of random matrices, we have a simple bound that we can achieve in the scalar case. Morally, we expect something similar to hold in the matrix case, but obtaining the right thing in the matrix case takes a much deeper identity at the heart of it. And that's why it's taken, I would say, quite a bit longer to develop these matrix concentration tools than it did to develop the corresponding tools for scalar random variables, which were already known in the 19th century. So our work today, as the title indicates, is to try to understand what happens when the function in question is not a sum, but a product. So a sum or an average is the situation dealt with the matrix Bernstein inequality that I said on the previous slide. That's the simplest function that one can possibly imagine. Here we are interested in products, which are, to my mind, maybe an equally simple function, and one that actually has a wealth of applications in a number of modern contexts. So a product of matrices is like a composition of operators. So whenever you're trying to analyze something that comes from composing random operators together, you naturally get something that looks like a product of matrices. So it turns out that random matrix products can be used to analyze linear dynamical systems. SGD, different types of stochastic optimization algorithms can be phrased in this way. People have used products of random matrices to understand the Jacobian of randomly initialized deep neural networks, for example. So there's a need for understanding products of random matrices, but I would say that what we didn't have before our work was maybe a clear understanding of how exactly we could lift concentration inequalities for products of scalar random variables to the case of products of random matrices. So let me tell you a little bit about what's known about questions of this type before I tell you about some more recent work and our results. So products of random matrices have been studied classically, and people have results showing what the large behavior of products of random matrices should be. So the earliest work in this vein is from the 50s and 60s, and it considers products of random matrices, IID random matrices, whose entries are positive and bounded away from 0 and infinity. And in that case, a series of works was able to conclude that there's a type of entry-wise law of large numbers that holds for matrices of this type. If you make the assumption that all of the entries are bounded on the same scale, then when you take the product of these random matrices, take the logarithm and normalize it in the appropriate way, you can see law of large numbers type behavior, and you get a CLT for the fluctuations of this object. Likewise, Berger in the 80s performed a similar analysis where the matrices were not assumed to have positive entries, but were small perturbations of the identity matrix. So of the form I plus epsilon I for some small matrix epsilon I. So that's actually going to be closer to the setting that we talked about today. And Berger obtained law of large numbers and CLT type results in that setting as well. What's important about these results is that they're entirely asymptotic, right? This is a great first step in the sense that it tells us what the expectation of these objects should be in the right sense and what their limiting behavior should be, but they do not allow us to extract any non-asymptotic concentration bounds of the form that we would like to use in practice. I'll also mention that there are two other strains of work that consider objects of this type. So the whole theory of free probability allows us to reason rigorously about products of random matrices in the large dimensional limit. So if I have suitable random matrices and the matrices grow, the dimension goes to infinity, then there's this notion of asymptotic freeness, which is a core idea in free probability that has been developed over the past, now 30 plus years. And this allows you to say rather precise things about what happens to the spectrum of these matrices if the dimension grows really, really large. Again, these are asymptotic results, but asymptotic in a different direction. Rather than taking a large number of matrices, they're taking a product of, say, two matrices as the dimension goes to infinity. It's also possible to get some explicit results if I require a lot of structure on my matrices. So if I require, for instance, that I have Wigner matrices, matrices whose entries are independent Gaussians, say, then one can actually sit down and compute what the properties of products of these random matrices are. But this is a Gaussian phenomenon, or a phenomenon that comes from having an invariant ensemble more generally. So all of these works are trying to reason about products of random matrices. Again, what's missing from our perspective is a bound with the simplicity and ease of, say, the matrix Bernstein bound we saw earlier that applies in a non-asymptotic setting with as few as possible assumptions. Okay, so the real starting point for our work was some recent work by Henriksen and Ward. So Ward's one of my co-authors on this paper, and with her student Amelia Henriksen, they came up with a really nice bound with an ingenious proof that's the first step in this program. So here's what they considered. They said, assume that the matrices are IID. They actually don't need that they're identically distributed. To go back to the question from earlier, I'm just going to say IID for simplicity here. But assume that the matrices are independent, and for now we'll assume identically distributed, and are bounded in spectral norm almost surely. Then we can consider the random product Zn, which comes from building a product of perturbations of the identity. So just to think about what we should expect this object to behave like here, think about something like stochastic gradient descent, where you are repeatedly applying compositions of operators that make small moves at each step. So Zn is a proxy for an object of that kind. We're repeatedly making small moves in the direction of xi, and we're forming a random product of all of these matrices. So what Henriksen and Ward showed was that Zn enjoys the following concentration bound, or the following expectation bound. They have a tail bound as well. So let's just parse this together for a second. So out front, you get some dependence on this quantity b, which is the bound that you pay, which is the bound of your individual objects xi. And then the scaling that you get is the one that up to logs you would hope for. Some logarithmic dependence on d and n, but otherwise the 1/√n rate, which is maybe the concentration that one should expect for this object. So we have some dependence on our almost sure bound b, and we get a rate that depends up to polylog factors as 1/√n.
So John,
yes.
Could I ask a question?
Yeah, absolutely.
This is Tim. Sorry, I don't know if something is showing up. So is it right to think of this as being close to what you would get if you think of this as behaving like just the first order part, like identity plus 1/n times the sum, and then the rest is kind of negligible?
So great. That's basically what I'm going to present on the next couple slides. So hold that thought, and if it's still not clear, we can come back to it.
Thanks.
So yeah, Tim asks exactly the right question. I'm actually going to show you the idea of the proof of this bound, because I think it gives some intuition for where this behavior comes from, and why possibly it's suboptimal, or how it could be improved. So the proof really is in the well-worn school of, if you have a hammer, everything looks like a nail. we have a tool, which is we understand by a matrix Bernstein inequality, concentration of sums of random matrices. So if we could pretend that this object, maybe along the lines of what Tim said, is a sum of random matrices instead of a product of random matrices, then we could do something. So the whole idea of the proof of Henriksen and Ward is to rewrite this as a sum of a lot of random matrices and carefully apply matrix Bernstein. So let's see how that goes. So as Tim says, we can think of this as a perturbation of the identity, and we multiply it all out. We have the identity plus a first order term, which is just the average of these matrices xi, plus higher order terms. And I've written the quadratic term here, but these of course continue. So, okay, if we were trying to apply matrix Bernstein, how would we try to bound this object or show that it's near the object that we want it to be near? Well, if I just look at this first order term, this first order term is a sum of independent, indeed IID random matrices. And so we know from matrix Bernstein that with high probability, this object concentrates, is near its expectation, just the expectation of an individual one of these random matrices X. So at the first order, this looks just like a sum of independent random matrices. And so with high probability, that term matches the expectation quite well. Now, if we try to do this for the second term, we already run into trouble in the sense that this is certainly not a sum of independent random matrices because some indices are repeated, right? So x1, for instance, appears in many of these summands. So these are no longer sums of independent random matrices. So it seems that already at this second term, I'm having a problem. I can't bound this using matrix Bernstein. So the observation of Henriksen and Ward was that it's true that this sum is a sum of dependent random matrices, but it can be partitioned into sums of independent random matrices, into n sums of independent random matrices. So what I can do, to say this in a slightly more geometrical way, the sum of indices that I am summing over looks like the edges of the complete graph, right? For each pair ij between 1 and n, I have a single term, xj, xi. But if I think about a complete graph, it's actually a well-known old theorem in graph theory that I can partition the edges of a complete graph into matchings. So matchings correspond to edges that have no intersections at the vertices. What this means in the language of our random matrices is I can partition this into sums where there are no repeated indices in any of the sums. And now each of these individually is a sum of random matrices. So each of them individually with high probability concentrates around their expectation. And it's not too hard to see that the expectation of each of these terms individually is expectation of x squared over 2n, because I renormalize by 1 over n squared, and there are n over 2 terms in each of these sums. Since I have n of these sums that I've partitioned, overall, I can hope with high probability that this term is of order expectation x squared over 2. Okay, great. That was good as far as it went. But my problems are just beginning in the fact that I was able to do this combinatorial decomposition for pairs of random variables in the second order term, but I'm going to have to do this forever. I'm going to have to do this for all terms in the expansion, at least until I can truncate it so it's small enough. And this seems like it's going to be increasingly a headache. Luckily, the good news is that people who work on graph theory already know the answer to this question. So it's a theorem of Bernsteins that any complete hypergraph decomposes into 1 factors, which is just a fancy way of saying that when I'm in the 3 term or the higher terms, I have just a complete hypergraph. Instead of edges, I now have hyperedges. But this hypergraph can be decomposed in exactly the same way that I decomposed the graph at the second level. So it turns out that each of these sums later on in the decomposition can also be decomposed into a partition which has independent entries. And so this object with high probability, again, concentrates around x cubed over 6. And if one completes this picture and then pays to union bound over all of the high probability events that I've described so far in this picture, you get the bound of Henriksen and Ward. So to summarize, to the question that Tim asked about, is this just what happens if you do the first order expansion? The answer is no. The first order expansion is easy, but everything else actually still contributes non-negligibly to your sum. And if you're trying to think about where that e to the b term came in the Henriksen and Ward bound, it's there precisely because the size of these random matrices that appear in the independent sums as I go further and further into the expansion grows. And so the sum of all of these sizes scales like e to the b. So the Henriksen and Ward argument, as I said, I think it's quite ingenious. It's the idea of really pushing as far as you can go, the idea of decomposing into sums. And you get something that looks like this. I will note also that a group out of Berkeley simplified this proof a bit recently and removed the logarithmic dependence on n, so that it's just log d over n in the second term, but the rest of the bound is still basically unchanged. So this was the starting point for our work, this work of Henriksen and Ward. And the question is this right? Is this the right bound that we should expect for this object? And maybe the first question that you might say, or the first thing you might say is, what about this exponential dependence on B? Is this correct or not? I would say that at least naively, it seems possible that this should be there. Because if you look at this object, right, if the xi's are really of size B in spectral norm, then Zn really could be of size e to the b in spectral norm. Because if all of the xn's, say, are b times the identity, then Zn really is of size e to the b. So originally, at least, it might seem like this e to the b dependence is sharp, because that's the scale of this object, Zn, in the first place. But that intuition isn't quite right when you think about it, because what I just described was a worst case bound, right? If all of the xi's are b times I, then this is indeed, I would say, the worst possible situation, right? They're all as large as they possibly could be. But we should really expect the size of Zn to grow not with the worst case size of these xi, but with the typical size of these xi. And if you write down what the scalar analog of this should be, that's exactly the difference that you see. If I form a product that looks exactly the same, except now I'm dealing with bounded scalar random variables, the concentration, the expectation that one gets looks exactly the same, except e to the b is replaced by e to the expectation of x. In other words, you replace the worst case bound by the typical size of each of the individual random variables. And so this is the question that motivated our work. Is it possible to change this e to the b into something that scales like the expectation of the matrices rather than their worst case bound? Just to show, somehow the slide that actually includes our bound is missing. Let me just see if I can find it. So let me just flash the results here. So here's our result, which, if you compare it to what's on the previous slide, looks exactly the same, except instead of e to the b, we have e to the mu. And the mu here is the size not of the worst case bound, but just the size of the expectations of the matrix xi. I will say that this result is actually a corollary of much more general results that appear in our paper. So take a look at the paper if you're interested in this more. But an important fact here is that just like the case with the matrix Bernstein inequality that we saw for sums of random matrices, apart from the log D factor, which is necessary, this actually matches the scalar concentration bound even up to constants. So we get a tail bound that looks exactly the same as the tail bound that you would get for scalar random variables, apart from the log D, which is the price to pay for the D-dimensional nature of these random matrices. So to convince you briefly that this improvement is important from E to the B to E to the mu, let me just compare what these bounds say in two different settings. So the most obvious case is when the matrices have zero mean, Henriksen and Ward still pay E to the B for the size of the almost sure bound on the random matrices xi. But when the expectation of xi is zero, mu is zero, and our bound pays nothing. So instead of exponential dependence on B, we get linear dependence on B. And even in the case where the expectation is not zero, the gains can be profound. So let's imagine, for instance, that we're back in the setting of covariance estimation. We're forming the outer product of, say, random vectors uniformly distributed over root D times the sphere. So the size of the operator norm of the matrices xi is D. So B scales like D, and the bound that Henriksen and Ward get is D times E to the D. But the expectation of xi is the identity matrix, which has operator norm 1. So E to the mu for us is 1. So again, instead of exponential dependence on D, we get linear dependence on D. So the point is that this is what looks like perhaps a technical improvement, but it actually gives a lot more content to these bounds, in the sense that there are cases where the Henriksen and Ward bound is vacuous because this E to the B term is far, far too large, whereas our bound still gives something meaningful. So before I go on to say anything more about the ideas of the proof, does anyone have questions about where we are so far?
Yeah, I have a question.
Yes.
So for this xi being a rank 1 matrix, with this prior drawn uniformly from the sphere, is the root of log D factor present in the bound?
Is the root of log D factor? Ah, I see. If
right.
These are all, you're saying if these perturbations are all rank 1,
Yes.
is the root log D factor present? It's a very good question. So the answer is, I believe in this case, yes, still. But if the individual, so as I said, our more general results deal not just with these perturbations of the identity, but just with products of random matrices, generally. And if the individual random matrices are not full rank, you don't pay for D. You pay for the rank of the, you pay for the rank of the individual elements instead. So if I actually had a product of low rank matrices, I wouldn't pay root log D, I would pay root log R, where R is the actual rank of any of the individual matrices. However, in this perturbations of the identity setting, I think one still does pay, one still does pay the root log D for perturbations of the identity, even if the perturbations are rank 1.
Okay, thanks.
And that's necessary in this case. Good. Any other questions?
Sure, yeah. Wait, can you hear me?
Yes.
Okay, cool. In the original Henriksen Ward proof, where exactly does E to the B pop out of the analysis? Is it from the coefficients in front of the expectations we get at the end of the day in the unit bound?
So let me back up to that analysis. So the key point is, if I looking at this right-hand column, these are the objects in question, right? That I want these to add up to be the expectation of my object. So let's, the point is that when let me back up actually. Let me back up to here. So how did I conclude that all of these orange boxes were close to their expectations, x squared over 2n? So I parsed them as sums of independent random matrices, where now my independent random matrices are of the form like xj, xi, right? Products of my original random matrices. So the point is that if I wanted to apply the matrix Bernstein bound, remember that that matrix Bernstein bound depends on the size, the almost sure bound on the size of your individual summands. And so if I assume a priori that each xi is bounded by b in spectral norm, then the best that I can say about these individual summands is that they're bounded by b squared in spectral norm, right? So the error bound that I get in doing this, so the error bound that I get in doing the decomposition of the first order term scales like b. The error term that I get in doing the second, the decomposition in the second term scales like b squared. And in general, for the higher order terms, the error that I incur doing the lth term will scale like b to the l. So the errors that I incur when I add up all of these give exponential dependence on b.
Cool, thanks.
Great. Any other questions? Terrific. So let's talk about some ideas in the proof. So let me just tell you that the proof of this stronger result turns out to be conceptually much more simple than the Henriksen Ward proof. And the idea is that we are going to try to think as little about matrices as possible. Instead, we're just going to phrase this as a problem involving random variables that take values in a particular Banach space. So let's define the Schatten P norm of matrices in the following way. So we'll define that the P norm of a matrix X is just the trace of the pth power of the positive part of the matrix X, by which we mean the trace of the P over 2th power of X transpose X. So if X is PSD to begin with, then this is nothing more than the pth power of the matrix X. In general, if X is not PSD or not even symmetric, then this is the right definition. So the point is that the set of D by D matrices equipped with this norm becomes a Banach space. And we will just try to directly exploit properties of this space. And essentially, the intuition is going to be, we want to understand how similar this Schatten P norm is to a Euclidean norm. And the important takeaway, which is a familiar idea to people who do probability in Banach spaces, is that if this norm, this Schatten P norm, is sufficiently like the Euclidean norm, what we'll mean by that is sufficiently smooth in a way that I'll make precise later, then good concentration will hold for random variables with respect to this norm. And so we're going to try to exploit this fact to prove concentration in various Schatten P norms, and from there extract the operator norm bound at the end of the day. So just to illustrate how these ideas work, I'm going to step you through the proof of a simpler claim, but one that already gives the high-level ideas of what's going on in the proof of not only the theorem that I mentioned earlier, but the more general statements as well. So let's try to prove the following thing, that if I have a bunch of IID matrices that are centered, that is, whose expectation is 0, and whose norm is bounded by B, almost surely, then the norm of the product scales like 1 plus big O of B times root log D over N. So in other words, the norm is 1 with a deviation that scales exactly like the object that we saw earlier, B times root log D over N. Notice here, by the way, that this is a far cry from the trivial worst case bound that we get just from assuming that the xi's are bounded. A priori, the size of Zn could be like e to the b. This says that the typical size of Zn is exponentially smaller than this. So we're going to try to prove this bound, and this will show where we use this geometric intuition that I mentioned on the previous slide. Okay, so how should we go about proving this? So if you've done anything with random matrices before, then you'll know that the operator norm is not so easy to work with, and it is much easier to work with various Schatten norms. So as a first step, let's just say that the expectation of this operator norm, well, I can pull the square inside the expectation by Jensen's inequality, and then replace the operator norm by the Frobenius norm, aka the Schatten-2 norm, just by using the monotonicity properties of these norms. So recall that the operator norm of this matrix is the largest singular value of the matrix, whereas the Frobenius norm is the L2 norm of the singular values. So we are just using an L infinity to L2 inequality here. Okay, so now let's remember the definition of Zn. We can develop this a little bit. So if I just focus on the very first factor in this random matrix, then it splits up into Zn plus 1 over n xn times Zn minus 1 and the whole thing squared in the norm. So Zn minus 1 is just the product of all of the last factors here. We've peeled off the first factor in this product. So what should we do now? Well, now actually we have something very natural to do, something very easy, which comes from the fact that the Schatten-2 norm, the Frobenius norm, arises from an inner product, right? This is just an entry-wise Euclidean norm, if you recall, for matrices, which means that we can do a Biasvariance decomposition of this object. So xn is independent of Zn minus 1. In particular, it's conditionally mean 0 when I condition on Zn minus 1. And the Schatten-2 norm arises from an inner product, which means that I just get something that looks like the expectation, the squared expectation and the expectation squared. This is nothing but a Biasvariance decomposition of this random matrix here, using the fact that xn is conditionally mean 0. Now what? Well, okay. Here, I have the matrix xn. All I know about the matrix xn is that it's bounded. So let me just pull it out of the Frobenius norm to conclude that this term is bounded above by 1 plus b squared over n squared times the expectation of Zn minus 1 squared, again, measured in the Frobenius norm. If I iterate this argument, I can just keep doing this, pulling off one factor at each time until I get down to the identity matrix, which is what we started with. And what I get then, if I unroll this bound, is I just get something that looks like e to the b squared over n times d. Okay. This bound is a far cry from what we wanted to prove, but it's already interesting. I mean, it already decays with n, whereas the worst case bound we had, which was e to the b, does not decay with n. So something better is happening here, but still this is far too loose. This thing isn't near 1. It looks like d instead. But before I go on, it's really important that everyone understands what was happening in this magic inequality or this magic equality in the last line where we did the Biasvariance decomposition. So are there any questions about the argument on this slide before I move forward?
I have a question.
Yes.
So this is Victor Preciado. I may be missing something silly. This is non-asymptotic, right?
Yeah.
So in the first equality that you have in the slide, inside the term Cn minus 1, don't you have to divide by 1 over n minus 1 when you're multiplying the x matrices?
Oh, yeah. So Zn minus 1, yeah, good. I didn't actually say what I defined it as. So Zn minus 1, I'm going to define as the product of I plus 1 over n, xn minus 1 down to n. So I'm not, yeah, that's a good point. So Zn minus 1 is not the analogous quantity with renormalization by n minus 1. It's just with renormalizing by 1 over n.
Okay, good.
Yeah, thank you.
Okay,
yeah.
Thank you.
And so if you hadn't done this is François Lever, if you hadn't done this decomposition on the last line, then what you would pull off is exactly 1 plus b over n, and you would get the e to the b.
Excellent.
Right, so the key is really this just to make sure I'm following. So the key is really this conditional expectation being 0 that allows you to square that b over n.
Yeah, this is exactly the right point. So if I look, you can see my mouse, right?
Yeah.
So if I just look at this line, one could try to do exactly the same thing, just noting that this matrix has size at most 1 plus b over n, and pulling it out in exactly the same way. But as Afonso notes, what one gets out of that is 1 plus b over n squared, essentially. And so instead of b squared over n up top, I just get b. And so I get nothing good. So this savings really comes from the fact that I can do this further decomposition. I get a quadratic dependence on n instead of a linear dependence on n, so that when I multiply n of these terms together, it's still small. Whereas if I had a linear dependence on n, then when I multiplied this n times together, I would get something that doesn't decay with n. I would get something of order e to the b. So that's the essential point here. Good. Any other question on this slide? Great. So the message here is just to summarize what we saw on the previous slide. Because the Frobenius norm arises from an inner product, it's the case that the expectation of Zn squared, when I write this in the Frobenius norm, can be exactly decomposed into 2 quadratic terms. And then by using the almost sure bound on xn after I do this decomposition, I get the inequality expectation of Zn squared is less than or equal to 1 plus b squared over n squared expectation of Zn minus 1 squared. And this was the thing that we could iterate in order to get a non-trivial bound for the size of Zn. Unfortunately, as I said on the previous slide, doing this in the Frobenius norm is just too loose. We get something that is not near optimal by doing this in the Frobenius norm, but unfortunately, the Frobenius norm is the only one of the Schatten P norms that arises from an inner product. None of the rest of them have this Hilbert space structure. So it seems like we're a little bit stuck, because this argument is nice and seems to give us what we need if we work in the 2 norm, but we can't work in the 2 norm if we want to get the optimal results. And the insight is that a concept from geometry of Banach spaces known as uniform smoothness allows us to mimic this argument in other norms, even ones that don't arise from an inner product. And so that's the only non-trivial piece of this puzzle, is to use this idea of uniform smoothness, which I'll now define, to mimic this argument in norms other than the 2 norm. So what is uniform smoothness? So just to motivate the definition quickly, let me remind you what I mean when I say that a convex function is smooth. So a convex function is smooth if it has the following type of quadratic upper bound, that f of y can be bounded by the linear estimate at x plus a term that looks at the deviation squared between x and y. So this is what smoothness means. This is just a quadratic upper bound that's familiar from convex optimization. So if I wanted to write this in a way that just isolates the effect of this squared term, I can say that this means that for any vector tau, for any other vector tau that I perturb x by, Jensen's inequality, so one way to say the next line is that Jensen's inequality, you can show that it's tight up to an L over 2 tau squared factor. In other words, that the average, if I do f of x plus tau and f of x minus tau, is less than or equal to f of x plus a quadratic term that scales with tau. So this second line is just a trivial application of the first line if I choose y is equal to x plus tau and x minus tau. So this is a consequence of smoothness for convex functions. And so motivated by this, we can define smoothness for a norm if the same inequality holds for the squared norm. So now here I have any norm on a Banach space, and I will say that that norm is 2 uniform smooth if an inequality exactly analogous to the one on the previous line holds for this squared norm. And the point here is that we want k to be a constant, right? Just like L is a constant in the previous line, we want some uniform quadratic control over this object. And this is what the definition of 2 uniform smoothness is. So this has been studied extensively in world of geometry of Banach spaces, this turns out to measure in a certain sense how well behaved your norm is. And well behaved in what sense? In the sense of comparing it somehow to how the true norm behaves, because this holds via the Biasvariance decomposition we said in the previous couple slides ago. This holds trivially for k equals 1 with the true norm. So this is the definition of true uniform smoothness. Why will this matter for us? Well, it turns out that the key property is that if you have a uniformly smooth norm, then something like a Biasvariance decomposition holds. So if my norm is true uniform smooth and I take and B is conditionally mean 0, then the expectation of the square of the norm of the sum is bounded above by these two quadratic terms. This looks very similar to what I had on the previous slide. And the proof of this is, well, let's just first pretend that it's the case that B isn't merely mean 0 condition on A, but actually symmetric. So B and negative B have the same law. So in that case, A plus B squared is the same as A minus B squared. So this expectation is nothing other than the expectation of this average quantity, which showed up in the definition of uniform smoothness. And then applying the uniform smooth requirement, we see that this object in the middle is bounded by A squared plus KB squared, and then we can pull the expectations inside. In order to get the general form of this, you can do an argument that's similar to this that involves a type of symmetrization. If you do naive symmetrization, it's hard to get the exact right constant K. You get something like 4K, but it turns out that the same constant that appears in the uniform smoothness definition is the constant that appears in this proposition, if you do the argument carefully enough. So the takeaway is if a norm is uniformly smooth, then it has a type of Biasvariance decomposition of this sort with an inequality sign. And now we come, as I said, to the only non-trivial fact that we use entirely, which is a deep theorem of Ball, Carlin, and Lieb, that the Schatten P norm is too uniform smooth. So this is really, in the same way that I said the development of matrix Bernstein required one non-trivial fact for matrix analysis, you need something that allows you to recapitulate your proof. This is the heavy machinery that we use, that the Schatten P norm is uniformly smooth with a constant that is exactly P minus 1. And this is the exact correct constant for the Schatten P norm. Or let's just agree to call this P for now, because it makes it easier to write on the next slide. So just to conclude the argument, this was the implication that we used for the Frobenius norm. For the Frobenius norm, we had an exact Biasvariance decomposition that held with equality, and then pulling out the xn allowed us to get this bound we could recurse. Uniform smoothness allows us to write down almost the same inequality, now with a less than or equal to sign, and with an extra factor of p in front of b squared over n squared. So uniform smoothness, we can write down almost the same thing up to this extra factor of p. And if we recurse this inequality via exactly the same idea, we get the following bound. And note that here, of course, the first term in this bound gets worse as p gets larger. That's a consequence of the fact that this inequality is looser as p gets large. But where do we gain? Well, we gain in the fact that we're no longer measuring the true norm of the identity matrix, but now the p norm. This is a familiar phenomenon for people who have worked in concentration of random matrices. By choosing p large enough, you can turn this d-dependent factor into something that just depends logarithmically on d. So this is the bound we get. And by optimizing the choice of p, we get exactly the claimed bound. So you have to choose something like p is equal to root 2 log d, root 2n log d over b squared, something like that. That gives you the optimum bound here, which is exactly the quantity that we claimed at the beginning. So the message here is that we had a proof that worked for the true norm. It relied on the fact that the true norm really arose from an inner product, and it didn't seem possible to do the same proof in a different Schatten norm. But in fact, these Schatten norms, even though they don't arise from an inner product, they are smooth enough. They're like the Euclidean norm in that sense. And that means that we can still write down the same expression, but with an extra factor of p. And everything follows from this observation. So all of the results in our paper, which hold for general products of random matrices, for inverses of products of random matrices, for adapted sequences, and so on, all of them come down to this basic observation that we can apply uniform smoothness to recursively peel off terms from this random product. So let me just conclude by saying some things that we would like to understand better, because this is not the end of the story for this product of random matrices. So I've been simplifying and thinking the whole time about IID random matrices, but if the random matrices are independent but not identically distributed, then there are phenomena that we can't yet capture. So one thing to note is that if the matrices are independent but not IID, then this term e to the mu in our concentration bound scales like e to the average of the norms rather than the norm of e to the expectation, e to the average expectation. So these are similar looking objects, but the second object can be much, much smaller than the first object. And one funny thing is that you can show by example that we can't always get the second object. Like this is too much to hope for in general. There are examples where this bound does not hold. But we also can find examples where this bound is the correct one, and this bound, which is the average of the norms in the exponent, is too loose. So I think that the big open question left by this work is, what is the right quantity to appear here? In the sense, we know it can't always be this, but this is also sometimes wrong. So there's something that we need that better captures the interaction of these random factors. And one sub-question of this, so something that turns out to be maybe display a little bit that there's something subtle going on that we haven't yet captured, is that if I have independent but not IID random variables, then it turns out that the product, the behavior of the concentration of the product, it matters a lot in what order these random variables come. There are some orders that concentrate much worse than other orderings. So some permutations where the fluctuations are much, much smaller. All of our bounds do not understand the difference between different orderings of these products. And so it would be really nice to get a bound that actually was able to show that some orderings are better than others. So that's all I wanted to say today. I wanted to leave you with this. We have a new bound for concentration of random matrix products. Unlike the bound of Henriksen Ward, it actually matches the scalar bound and scales with the right quantities. And maybe I hope represents a first step in getting a sophisticated understanding of products of random matrices as we now have for sums of random matrices. So thank you all for your attention, and I'm happy to take any questions.